Hi, everyone. Thank you all for taking the time to attend my talk today. My name is David McDonald. I'm a software engineer at Velexity, where I work on our Volcano memory forensics analysis tools. And today I'm going to be talking to y'all about detecting, deobfuscating, and blocking fileless malware with TreeSitter. So I think the best way to kick things off would be to show y'all Windows AMSI interface in action. For anybody who's not familiar, AMSI is the Antimalware Scanning Interface on Windows, and it's really PowerShell's first line of defense against malicious scripts. So anytime you run something in a PowerShell interpreter, it's going to get handed off to the AMSI provider DLL. In this case, the default is called mpoav.dll, and it has a method called scan buffer that is going to read the contents and determine whether or not it is malicious or clean or unknown. So what you see here is a setup that is typical of a lot of attacks where you invoke REST method, pull down a PowerShell script from a C2 server, and then in the second part, after I demonstrate the actual script contents, you'll see that it is going to be piped into IEX, which is an alias for invoke expression. So for this first sample right here, this is a run-of-the-mill PowerShell-only AMSI bypass that I pulled off of GitHub. It's really popular. It has probably hundreds, if not thousands of stars, and it does a whole lot of nasty stuff. It's going to create an API for accessing get proc address, load library, virtual protect. It's going to load the actual AMSI provider DLL into memory, patch its DLL get class object function, and then deactivate any initialized AMSI providers. And after that, it will, in theory, be able to do whatever it wants for the remainder of that PowerShell session. So if we pipe this into IEX, we can see that AMSI did its job. It detects malicious script content and it blocks the script from executing. So over in the event logs here, I have no idea why I can't click on that. You would see event ID 116, which is Windows Defender has identified malicious script content and blocked it. Now let's take a look at another variant of this, which is bypass 2. This is the same script, but with a few tweaks. I took that definition of types that is going to, define get proc address, load library, etc., and I split it into 5 different variables, concatenated it together, and then updated these like shellcode definitions here as well. And let's try running this instead. So AMSI did not detect that. And now if we go to rerun the first script, it just allows that to execute as well. So we can see that AMSI has been disabled for this PowerShell session. So that's not exactly what I would call a high degree of difficulty attack. And the way I was able to do that is by using this tool called amsitrigger.exe and passing it the first script. And I haven't read the source code too closely, but what I'm pretty sure it does is just bisects the script piece by piece until it finds the strings that are going to trigger AMSI. It hands off each chunk of the script to AMSI, says, scan this and let me know if it's bad. And then if it's bad, it prints it out. So you know exactly what you need to go modify in your script. And then you can just do it. So AMSI does a great job against that, but struggles mightily against even simple obfuscations like this. They didn't even reorder any of the strings. This is from the actual GitHub repo from November of last year. It says system.management.automation.amsi utils is being flagged now. Just do a basic obfuscation of it like the example and it works again. And there are several popular open source obfuscation toolkits. Invoke-Obfuscation being most notable among them. Attackers are lazy and they will use these tools if they are known to work. And the reason they work so well is because scanners are just not aware of the actual programming language syntax. They're just scanning unstructured streams of bytes. That makes it extremely effective against anything that is signature-based. Even sophisticated Yara rules can be bypassed pretty easily. And these obfuscation tools have the other side effect of slowing down your analysis, of understanding what might have happened on the machine. Even script block logging sometimes isn't going to show you everything because token and string obfuscations are not deobfuscated within the 4104 script block logs. This is an example of a Yara rule that is attempting to detect obfuscated PowerShell. So you've got three strings. One of them is .invoke, which is looking for like invocation of dynamically constructed methods on objects. And you've got two other strings that are components of format strings. And the condition here is that it needs to hit at least 10 or 11 of all three of these in order to flag. So you can see why a lot of things might slip past something like this if you're obfuscating a smaller script. So you're really just like doing your best against something that you're not really equipped for. And to the naked eye, it looks pretty obvious that this is bad. Like if you saw this coming through your event logs, you would be like, that is bad. I don't want that running on my system. I have no idea what that is. And that's because we as humans understand programming languages. We, in our minds, can sort of see a syntax tree and know that like a lot of bad stuff is going on. This is another one that I looked at when I first started working on this back in early 2024. And it got me thinking, okay, I want to do two different things here. One is design a better way to scan for these things. And another is to, if possible, just unwind these obfuscations altogether. And that's what I was able to do, is design a tool that can, piece by piece, go through the script, rebuild as much of the source code as possible, and provide you with actionable intelligence. This is actually slowed down greatly just for demonstration purposes. I put a call to like sleep in between each iteration. But in reality, this is a very fast process. And the key to this is what I called atomic operations. So what do you really need to do in order to understand that this is a string that you need to glue back together? Well, you need to know that the left side is a string literal, like an actual node in like the programming language syntax tree. And you need to know that it occupies bytes 0 through 4. You need to know that this is an addition operator occupying bytes 5 through 6. And you need to know that this is another string literal occupying bytes 7 through 11. And finally, you need to know that all of these together are forming an additive expression occupying the range 0 through 11. So if you have programmatic access to all that data, then you could, in theory, just do what you need to do to fix that up and make it a single string. And that's where a tree setter comes into play. A tree setter is a parser generator originally developed for the Atom text editor and is now fully integrated into NeoVim. So you install your language grammars and you automatically get AST support for whatever language you're working with. The grammars are written in a kind of funky JavaScript dialect, converted to JSON, and then transpiled into C source code for a super fast, lightweight parser that allows you to get updates to the actual syntax tree on every single keystroke as you edit the document. There's strong support for most mainstream languages, and there is an active development community of less common languages even. And my first exposure to this was through queries, because I was watching YouTube one day and there was a video on how you can get highlighted SQL syntax inside of your embedded strings in another programming language. I do a ton of work with Postgres queries. So I was like, this is something that I really would love to have. You can get instant feedback on whether or not the query you're typing within a string is syntactically valid. If you look down at the bottom there, you can see that although we are in a multi-line Python literal, the text is actually highlighted as syntax because I have told NeoVim through the tree sitter API that I'm looking for anything that matches query should be highlighted as SQL, more or less. So it lets you do all kinds of fun things like your language injections, also advanced code navigation, automated refactorings. There's actually like a really cool ecosystem of tools that has cropped up around this. Here's an example of what a query would look like in Python. I chose Python here because it has a very simple grammar and it's easy to understand. On the right side, you have your actual source code. Note that ID here is not part of the source code. On the left side, you have the syntax tree itself on the bottom left. You can open this by running the inspect tree command in NeoVim. And on the top left, you have a query. So this says I'm looking for an assignment where the left identifier, which I'm going to call ID in a named capture, is equal to foo. And tree sitter within NeoVim says, hey, okay, that's what you're looking for right there. It's a left-hand identifier named foo. Here's another example of looking for a binary operation between two strings. So like hello plus world. On the left side, it's a strict equality check here in this clause. On the right side, it is a regular expression match. So it can be WORL, it can be world, it can be WORLF, whatever you want it to be. And it'll match that and label it as hello world binary. So it was fortuitous that I started looking at this at the same time that I had been exposed to some of this obfuscated PowerShell malware, because I was like, okay, if we can find out grammar for PowerShell, then maybe we can start doing some really cool stuff in terms of detection and maybe deobfuscation. And that's when I saw that Airbus CERT team had resurrected the PowerShell grammar from the Microsoft repo grave. Theirs was pretty abandoned and not functional anymore. So once I got that installed and started playing with it, I was able to start doing things like detections. So this is an example of PowerShell scanning for something that you wouldn't really want to see in your code. This looks for the command invocation operator, followed by a parenthesized pipeline containing a format expression in the middle. You generally would not want to see something like this in your source code. It's kind of a tell. And what I love so much about this example is that you're looking for basically a dot and then something on the inside that you really can't write a regular expression for easily. I mean, I would say maybe even at all. So what are you going to grep for the letter like period? I don't think that's going to work very well. But when you scan for this with something equipped for it with tree sitter, it sticks out like a sore thumb. So I used a tool called tree grepper, integrated the PowerShell grammar into it, and started searching across a repo that I had just like applied obfuscations to, specifically the format string obfuscation to see how much I could come up with. That Yara rule you saw earlier had 86 hits, and tree grepper had 616. And not only that, but it pointed out the exact contents of each node within each file syntax tree that contains this. So I was like, that's awesome. That's a really cool and simple detection for something that you wouldn't want to see in PowerShell code. So to get to this, it required a few more steps, well, several more steps, which was figuring out all the different types of obfuscations that I needed to unwind. Now, there are existing methods for deobfuscating PowerShell. This is one of my favorites. It seems funny, but it actually works sometimes, especially on like if you just feel comfortable running it in like a Linux sandbox with the PowerShell interpreter, you can do it in there. But The problem with that is, number one, it's kind of a heavyweight solution. And number two, it doesn't really scale well when you have potentially thousands, tens of thousands of endpoints. That's something that we think a lot about at Velexity is how can we make our solutions scalable? There's also Revoke-Obfuscation. This isn't really a deobfuscator as much as it is like a detection engine, but it's written by the same guy that wrote Invoke-Obfuscation, so I assume it works well enough. And then there's tools like PS Detect and Power Decode, which are PowerShell-based tools, but they are for deobfuscation only. It's a heavyweight solution. You have to run it in a sandbox since you're actually using a PowerShell interpreter. Doesn't scale well across large data sets, entire enterprises, and it does not handle corrupt data. So if you pass a PowerShell interpreter something that has even a single character off and can't form a valid syntax tree, the interpreter is just going to choke, and you're going to be left trying to manually touch up the script. So when you pull things out of memory, for instance, you don't necessarily have that guarantee of integrity. And this is what these tools would kind of do is, my God, stay. It would override the invoke expression command, for instance, and have it just write host whatever the parameters are. So instead of executing a script block, it would just print it to the screen. So you're kind of taking a PowerShell interpreter and trying to patch it back to a point where it doesn't do bad things. So yeah, if we look at the challenges associated with detecting this kind of malicious PowerShell, you've got all kinds of different data sources it can come from. It can come from file collections. It can come from script block logging, C2 endpoints that you might pull it down from, cache files in memory, process memory, kernel memory, free memory, just address spaces, or even network traffic in some rare cases. And again, you want it to be scalable. Ideally, you'd have a solution that is cross-platform and very fast, and something that can process a ton of data very quickly. So Invoke-Obfuscation uses several different types of obfuscations. For instance, you've got your token obfuscations, AST, string, etc. Token obfuscation is really, really easy to detect with TreeSitter. Like injection of ticks within a command name. I need to quit clicking this. So this might actually throw a signature-based scanner off. You know, you're breaking up the characters that it might have as part of its regular expression. But what's cool about TreeSitter is that you can actually look for command names and find ones that contain these things. So instead of being a method of evasion, it becomes a major tell. And this is how easy it is. You can just write this query right here, like look for a command where it matches any characters with a backtick followed by any characters, and it'll highlight it perfectly for you. Here's another example of a token obfuscation, which is the splat concat method of basically breaking things out into different string parts and then executing them. Very easy to detect as well with a TreeSitter query. And then you have AST obfuscation, where you manipulate the ordering of the AST nodes. This doesn't really affect TreeSitter's ability to query substructures because the queries are not sensitive to the ordering of the nodes necessarily. And this is string obfuscation, where the entire command gets like broken down into a string, and ultimately it's going to get invoked with a IEX invoke expression, which is being constructed from the PS home variables here. So again, you've got the command invocation operator. You can look for the command invocation operator with a pipeline of concatenated strings, including variable names. And you can use typecasting also to try to mess with the data types. So you've got a format string, but you're going to build the actual characters by casting integer values up. Super easy to find character casting as well. So what I did was I wrote queries that would find each of these individual operations, and then wrote a callback to perform when each of them is found that would update the syntax tree with the value that I thought was more appropriate. So if it's casting an integer to a character, just replace it with the literal text of the character. If it's two strings concatenated together, just make it one string. And you just basically execute all of these queries in a loop until you can't find any more of them, and then you stop. Another thing that's useful is because you have access to the variable names, one thing that's really common in PowerShell obfuscation is for attackers to give variables really garbage names like B5DAR2. When you have many of these in a script, it increases the cognitive load of you trying to understand it. So you can find all the variable names very easily and just replace them with something like this. This is like this is the same library that like names Docker containers is what I use to generate that. So once you have all these things together, you can do some really advanced unpacking. This is creating a script block from basically a gzipped base64 string. And within the base64 string, it's been cut into pieces, like you can see right here. You've got format strings going on. You've got the call to from base64 string. You've got a gzip stream, and then you've got script block creation. And the cool thing about the queries is that if you design them right, they won't execute the callbacks for from base64 string, from gzip stream until all of the other format strings and concatenations have been worked out. So this is that exact sample being unpacked using the same method, and finally you get okay, can't beat it. There we go. You end up with the actual script that you're trying to find, which contains a base64 string being converted to a byte array. And yeah, much easier to understand. Another huge advantage that TreeSetter has is error recovery. It can handle incomplete or broken scripts. It just replaces wherever it stops parsing valid source code with an error node. So it allows you to actually deobfuscate it, even if it's not a completely valid script. So this right here is an attempt to run a broken script in PowerShell. You can see that it's going to just choke on the missing terminator. And here is the same script being deobfuscated. Even though it doesn't form a fully valid syntax tree, enough nodes are valid that it can still do work. So I had gotten to the point of that level of deobfuscation, and around the same time, the same team that had resurrected the PowerShell grammar, Airbus Cert, came out with this -1 library end tool. And it is really cool. And I was looking at the source code of it. What surprised me was that they took a completely different approach to things. There was not a single query used in the entire library. And instead, it's based on a depth-first tree traversal combined with a visitor pattern. So you have rules. Well, you have this rule trait, and you have rule mute. Rule is for just visiting the syntax tree and performing an action on each node. You have two opportunities to do something. You do it when you enter on the way down through the traversal and when you leave again on the way up. Rule mute is very similar, except you're allowed to actually mutate the nodes themselves. So you can change the text, delete them, do whatever you want to do. So this is another GitHub page. It's a PowerShell obfuscation Bible, and I really enjoyed reading this as part of this work because a lot of the things that they call out as like excellent obfuscation techniques are actually extremely easy to detect with TreeSetter. This is an example of low entropy obfuscation where they've assigned these random variable names. Again, that makes it really hard to interpret. But the problem with that is that it skews the entropy of the file and will set off some scanning engines. So you do something like this instead, just create giant variable names full of Fs. And now, you've got a low entropy document, technically speaking. So at this point, I was like, okay, we've got a really awesome Rust library, the ability to write rules, and also Windows for Rust has been coming along. So I was like, what if we can give AMSI a boost and merge these two things together? So after much pain and suffering, I was able to get a working AMSI provider written in Rust and load it onto a Windows VM. Let's see. All right, so on the left side here, I'm basically tailing a log file that my own custom AMSI provider is going to write to. And on the right side, I again have a PowerShell session, and it is going to execute some payloads in the exact same manner as before, where you download it via Invoke-REST method and you pipe it to IEX. So there's our original script. You can see on the left side, it logs my invocation of Invoke-REST method. You get the hash, you get the total bytes, and you can see that the source of it is from memory. Now, when we run that one, again, the default AMSI provider detects that as malicious, as it should, and it gets logged in my log here. But let's look at that second payload that was the original AMSI bypass. This time it gets flagged, and this is because of the custom AMSI provider DLL that I have installed alongside the systems provider. So if you look at the output here, it's not the nicest log format because this is just a demo, but you can see that it had a string match on system.management.automation.amc utils, and it has dumped the decoded, deobfuscated source code right here. You can see the original declaration of all of the kernel 32 functions. You can see the original shell code. It has even forward substituted the variables into this byte array here and completely deobfuscated system.management.automation.utils. So now we've got an AMSI provider that has a real edge in that it does understand syntax trees and can start detecting things at a more advanced level. So if we look at that low entropy obfuscation again, let's take a look at a sample that tries to do that. So this is a really simple example. I didn't go too crazy with it, but you just define some variable names that are long and have a single character and are, again, not something you would typically want to see running in your PowerShell environment. Something is up with that. And when we run that, why am I not seeing something here? There we go. There was just a delay. You can see that it has flagged variable entropy in 4 different parts of that script. So again, one of the things that they considered a powerful tool of evasion is now making them stick out like a sore thumb. And that's a Shannon entropy calculation below a certain threshold for variables that are of a certain length. That way you don't get like false positives on small little variables. Again, with the quote injection, it says you can obfuscate commandlets by adding single and or double quotes in between their characters, as long as it's not at the beginning. And it's super effective. For example, the expression IEXPWD can be substituted with all of these different variants, all of which might be effective against your traditional scanning engines, but are going to be easily spotted by a syntax-aware scanner. Another cool feature is because you can detect comment nodes within a syntax tree, it renders this entire technique irrelevant as well, because you can just bulk delete comments. Comments are another way that entropy values are commonly tampered with. I've seen lots of samples on, for example, Malware Bazaar, where you have a gigantic script that encodes like an encrypted executable, but to affect the entropy of the whole document, they have put in just, tons and tons of comments. So this got me thinking about, well, why let our good Yara rules go to waste? Threat intel teams spend a lot of time and energy developing them. And I think we can actually make them better, because now you don't have to wait for these kinds of things to show up in your process memory and other places in your environment, like after the compromise has already happened. And the reason we can integrate the two is because -1 actually does something really cool as well, which is it assigns an inferred data value to a syntax tree node. So not only can you see that, well, some rules will do that. So not only can you see that a syntax tree node has, a byte array, but you can actually check its contents. And in this case, you can initialize a vec in Rust, check to make sure they're all like below the size. Every item in that array is below the size of a unsigned 8-bit integer or a byte. And if that's so, run a Yara rule on it. So here is an example of a very basic encoded portable executable. This is like the simplest Yara rule of all time, but it's really effective in this context because you kind of want to know if there are PE files embedded in your PowerShell scripts. So here we have like a function that is defined that is going to essentially do like an unhexlify operation on this string here and create a byte array of, you can see the 45DA is like an MZ header. So when we try to run that, it gets blocked by my AMSI provider. And the reason is a Yara match right here. And the rule identifier is PE. So we were able to scan with a Yara rule, even though we're not looking at raw bytes. And what's really cool about this is that all of these rules kind of are force multipliers. For each one that you add, the whole engine gets better and better. So here's that same thing with Invoke-Obfuscation applied to it. Tons of obfuscations. And when we run invoke expression on that again, once again, it gets blocked. The deobfuscated contents are printed at the bottom here. And we have a Yara hit on that one as well for is PE. And here's, again, another trick that I've seen a lot of is trying to avoid detection of these like hexlified sequences, because some Yara rules will look for those kinds of things by doing like string replacements or reversals. You can actually detect methods written on a string literal in PowerShell, complete the operation, still infer the correct value of the syntax tree node as a byte array, and run your PowerShell or your Yara rules on it. So again, deobfuscated, the script appears down here, and we see our Yara hits. Make sure I'm not overlooking anything here. Oh yeah, this is this R77.ps1 is an example of a payload from the R77 open source rootkit. And I thought this one was fun because it does a very basic, very basic string obfuscation. So character casting, concatenation, does a very good job at scrambling the script contents, but ultimately is going to be deobfuscated very easily. They've got the backticks included in the command names, as you can see. I'm not going to run that one in the actual AMSI provider because Windows is pretty keyed in on the open source rootkit and is just going to like pitch a fit. But this is the deobfuscated script content. So you can see that it's very effective against those types of obfuscations. All right. And that's what I've got for today. Thank you all for your attention.